In the last video, we left off with the consumer's problem giving us an optimal bundle at the point where marginal rate of transformation is equal to the marginal rate of substitution with full expenditure. This optimal bundle depended on the indifference curve and the budget line, which is constructed from income and prices. And since our solution to the consumer's problem depended on these shapes, it's really natural to wonder what happens to our optimal bundle when prices and incomes change. So that's the question we'll pose in this video. Let's consider the consumer's problem with the standard Cobb-Douglas utility function. And let's set alpha equal to 1/2 for this example. The solution to the consumer's problem gives us an optimal bundle of QA and QB, which depends on PA and PB with Y. We graphed the consumer's problem with the budget constraint and the indifference curve, finding that the optimal bundle we solved for happens at the point where the budget line was tangent to the indifference curve. And in the utility maximization problem, we had 3 levers we could pull on. We could change the problem by moving income up or down, the price of A up or down, and the price of B up or down. In this video, we're going to trace out what happens when we move around each of these income and price variables. As a baseline, we'll set PA equal to 1, PB equal to 2, and we'll start with income equal to 120. Let's first ask the question, how would a change in income influence the individual demand curves? When Y is equal to 120, the optimal bundle is 60 and 30. Shifting income inward to 80, our new optimal bundle shifts into 40 and 20, placing us on a lower indifference curve. This probably makes sense with our intuition that a lower income means we won't be able to reach the optimal bundle we previously were able to. And then when we increase income to 180, our optimal bundle again shifts out to 90 and 45. So again, with an increase in income, we're able to achieve a higher bundle and a higher indifference curve, probably again matching our intuition. We can look at a range of income levels, mapping out the relationship between Y and the optimal bundles. And as a side note here, this isn't the relationship between just any bundle and income. It's specifically the relationship between income and the optimal bundle. This relationship you're seeing is what we call the income consumption path, the path denoting the optimal bundles of goods as income increases when we hold prices constant. So what does the income compensation path tell us? Both QA and QB increase in response to an increase in income. But there's another way to set up this relationship between income and quantity demanded, what we call the Engle Curve, which is the relationship between income and a specific bundle. Here, let's just isolate QA and map out what happens when we shift income in the same way we did for the income compensation curve. You might have flashes of intro topics in the back of your mind here. A positive relationship between income and quantity demanded means we're looking at a normal good. And if the Engle curve bent backwards, this would mean it would be an inferior good. If I were to ask you to use just the information we have available in this video, would you be able to calculate the income elasticity of demand for any point on the Engle curve? Okay, now that we've walked through variations in income and observed what happened to our quantity demanded, let's do the same thing but for prices, which is going to give us our individual demand curves. So let's set PA equal to 1, PB equal to 1, and Y equal to 180. When the price of A is equal to 1, the budget constraint isn't particularly steep or flat, and we choose a quantity of A that's equal to 90, with the quantity of B also equaling 90. As we move to a price for A of 2, the budget constraint becomes steeper, since we're less able to afford QA, moving us to a QA of 45, while at the same time lowering our indifference curve. And since the marginal rate of transformation is relatively steeper than it was before, the marginal rate of substitution at the tangent point is also relatively steeper. And finally, at a price of 3, we see a further 1 steepening of the marginal rate of transformation and the marginal rate of substitution, and 2, a shrinking of QA to 30. Let's just quickly animate a few of the prices to trace out the individual demand for QA. This is the classic relationship between price and quantity, what we've called the individual demand curve for QA. And we can do the same tracing for QB by varying the price of B in the consumer's problem. And similar to PA, moving PB maps out the individual demand for QB. At this point, you may have noticed a nuance with analyzing the impact of a price change when we hold income, preferences, and the price of other goods constant. When we change prices, not only did we change the relative prices, the marginal rate of transformation, but we also changed how much we would need to spend on the original bundle. If the price of one good went up, we would need to spend more to buy the same bundle. And if the price went down, we'd need to spend less. Because of this relationship, economists make a subtle distinction between two effects influencing how quantities change. The first is the substitution effect, which is the change in the quantity of a good that a consumer demands when the good's price rises, holding everything else constant. The second effect is what we call the income effect. This is the change in the quantity of a good a consumer demands because of a change in income, holding prices constant. Part of what we care about is the effect of a change in prices without changing which indifference curve we live on. This is the substitution effect. How much does a change in relative prices move us along the indifference curve that we already live on? And part of what we care about is how much the change in prices moves us across indifference curves. This is the income effect. For our normal good, QA, we get both the along and the across effects. The along component, the substitution effect, sort of rotates us along the indifference curve. We stay on the indifference curve, changing the marginal rate of substitution and the marginal rate of transformation according to the new prices. The across component, the income effect, moves us across indifference curves with a parallel marginal rate of transformation, which moves us to a lower utility level, matching our original expenditure. The total effect of the price change, captured by the Engle curve and the income compensation curve, is the movement from the starting point to the ending point, and is a combination of these two effects. Okay, if distinguishing between these two effects in the price income quantity models we've developed so far feels hazy, you're in luck. This fuzziness you're feeling at this moment is exactly what motivated John Hicks to develop what we call the compensated demand, or Hicksian demand, after John Hicks. So far, our individual demand, what we sometimes call Marshallian demand, allows consumers' utility to vary as price changes. When prices go up, the budget is more constraining and we drop to a lower indifference curve. When prices go down, the budget allows us to jump to a higher indifference curve. Compensated demand, though, sometimes what we call Hicksian demand, holds utility constant, just moving us along the indifference curve, observing how changes in price affect the quantity demanded. Instead of holding income constant, compensated demand adjusts income to hold utility constant. At this point, you might have synapses firing here if you're noticing the similarity between the idea of expenditure minimization and Hicksian demand. The compensated demand, or Hicksian demand, takes a fixed utility U bar and new prices, PA and PB in this case, and gives the solution to the expenditure minimization for that particular utility. This is equivalent to finding the tangency between the indifference curve defined by U bar and the budget constraint by varying Y. The two ideas are so closely linked. We can find the compensated demand curve by taking the partial derivative of the expenditure function with respect to the good we're looking at. We can also observe this decomposition of a price change mathematically via the Slutsky equation. To see this, let's start with an identity setting the income Y in the Marshallian demand such that it returns the same utility level U bar that defines the Hicksian demand. And this is an identity. If we differentiate this identity with respect to PA, we get the following relationship, which decomposes the total effect into the substitution effect, which is the movements along the indifference curve captured by Hicksian demand, and the income effect, which is movements across indifference curves captured by changes in expenditure. We already know that the derivative of the expenditure function with respect to the price of A is equal to QA, which is the compensated demand for QA. Often it's easier to think of the Slutsky equation in terms of elasticities. So to see this, let's multiply both sides by PA over QA, and multiplying the most right term by E over E, which is just 1. Simplifying here in a very special way gives us this thing. This looks a lot like a set of elasticities. On the left, we have this elasticity we haven't defined yet, what we call the substitution elasticity of demand. Then we have price elasticity of demand. Then we have income elasticity of demand multiplied by the expenditure on QA.